The open source community is full of projects with very bizarre and cryptic names, and they often do a poor job of explaining what that technology is used for or who is likely to use it. And for that reason, it may surprise you to know that containerization is well named and aptly describes what that technology is for. In its simplest form, a container is an environment that holds or contains all the variables, definitions, and libraries that your application or process needs to be self-sufficient. The result is a very portable, modular environment for any type of code that you need to move across various environments, be that from on-premises to public or private cloud, and it allows you to be very modular in design as well, so that you don't need to include unnecessary operating systems, drivers, or runtimes. Everything that your process or container needs to run is self-encapsulated within that environment. And for that reason, we often like to think of containers as a sandbox environment for your applications and processes. For many of us, the technology known as Docker is nearly synonymous with the concept of containerization itself, which really is a testament to Docker's popularity and the dominance that it has in the marketplace today. Docker is a container runtime technology that was proposed by two Y Combinator alumni grads in the year of 2011 and further released into the open source community in March of 2013. A few months later, Red Hat and Docker officially announced a collaboration focused on things like Fedora, Red Hat Enterprise Linux, and OpenShift, cementing a deep and long-lasting partnership that continues between the two organizations to this day. By 2018, it was estimated that over 83% of the marketplace, including everything from small business to large enterprise, are relying upon Docker as their containerized service of choice. So what is it that Docker provides the end user? Docker in its simplest form is an operating system level virtualization for the development and deployment of containerized code. The content of these containers is entirely definable by you, and we'll get into how these are built in a moment. But for now, understand that the key value proposition of containers in general, for things like Docker, but also its competitors, is the simplicity of its design, the portability across the widest range of infrastructure and platforms, and the repeatable, consistent patterns that emerge for how you can deploy containers in containerized environments. Much like how you'd utilize wrappers and containers in a kitchen household environment to separate raw meats from produce from cooking supplies, you can also utilize and conceptualize containers in the software sense in much the same way, allowing applications, code, and their dependencies to exist independently from the underlying operating systems and hardware that those containers are deployed onto. The container lifecycle and the lifecycle of the processes running within that container are by design very closely coupled with a Docker containerization system. So for example, when you instantiate a container, all the processes that are defined within it will begin executing tasks or performing different threads that may in turn kick off spawning other daemon services, generating other processes within the container, and so on. The rule of thumb that you need to keep in mind as a designer and user of these containerized applications is that the complexity and scope of these environments are entirely definable by you. For those of you familiar with virtual machines or VMs, you may be wondering at this point what distinguishes a container from a VM. After all, virtual machines provide hypervisor level isolation, and containers and VMs at this point sound like they're trying to achieve the same goal, which is encapsulating and partitioning from one another different processes and services. But ultimately, the key difference is that containers like Docker are dramatically more lightweight and flexible than you would find with a virtual machine. VMs require the complete operating system to be part of the isolated environment. With containerization, you're able to strip down that operating system to the bare bone minimum of what you need to run that process or that application. So you're able to take a much smaller footprint and therefore a much smaller install size with the containers that you define with things like Docker. And this has great implications for those that are looking to make their applications more portable, as there's less data to move across different environments, but it also means that the environments can be pared down to the most simplistic and elegant form of that code and the supporting runtimes and environments that it needs to perform its job. Virtual machines also have a static or fixed amount of memory and compute resources available to them, and this has implications for your agility as an application designer and for an administrator of these applications. With containerization services like Docker, you have the ability to elastically provision more resources for more memory and more CPU over time, so that as an application garners more interest or more users are hitting that application endpoint, you can provision those resources elastically and dynamically to keep that process running and keep those users satisfied. Docker keeps all this complexity in check by ensuring that each container is packaged with all the dependencies that it needs to run. This means that when you run a containerized environment like Docker within an operating system, you don't need to install anything to the local environment. Docker runs above the kernel and operating system level and comes equipped with all the components, dependencies, libraries, and drivers that it needs to perform its task within that containerized environment. In its simplest terms, a container is defined by three separate components: the binaries in the stripped-down operating system needed by the environment, usually something like Linux, any utilities, tools, and scripts that that application needs in order to perform its task, and lastly, if that app needs to talk to anything in the outside world, you should also include things like the infrastructure definitions, the networking topology, and other pieces of information that you would need to facilitate communication between multiple container environments. A nice side effect of this modular containerized deployment method is that since you're not installing or anything local to the underlying operating system, you can just as cleanly remove Docker containers altogether as how you brought them into the environment. For application developers, this has a very powerful and often unexpected side effect, which is that as you're testing new iterations of code, with every change and every version, you're likely having to introduce into that environment new libraries, new drivers, and things that ultimately pollute the underlying operating system and the hardware that that code is running upon. By utilizing a containerized environment such as Docker, you can cleanly and easily remove and add in these containerized test dev environments as you iteratively approach the finalized release of your production code.